Welcome to this explainer. Today we are unpacking the invisible mechanics running our entire modern world. We're going to trace the line from your smartphone's microscopic brain all the way to the cinematic lighting in premium commercials. Let's dive right in.
To kick things off, let's ask ourselves a pretty unexpected question. How in the world does raw computing power connect an 80s medical tragedy to the photorealistic 3D animations we see today? I know, it sounds like a massive stretch, but as you'll see, they are actually bound by the exact same underlying technological DNA.
Part 1. The CPU's invisible DNA. Let's take a look at the microscopic foundation of computing.
The sheer scale of human progress here is literally staggering. Think back to 1983. A chip like the 6502 inside the classic Apple IIe had just 4,528 transistors. Fast forward to today, and the modern M1 chip, which might be powering the laptop or phone you're using right now, packs in a mind-blowing 16 billion transistors. That microscopic architecture handles 3 trillion calculations a second, yet despite that 10 billion-fold increase in power, the foundational principles remain exactly the same. To really grasp how this architecture functions, I want you to picture an incredibly fast, automated robot inside a massive library. This library, that's your computer. The huge rows of bookshelves represent your long-term storage, your SSD. The cart moving books around is your short-term memory, or RAM. And that small table where the robot actually sits to read the books, that's the CPU's ultra-fast cache memory. The robot itself acts as the control unit, rapidly pulling books to the table, reading them, and using a calculator to find the exact answers. And this robot strictly follows the CPU's technological DNA, which is a relentless 3-step cycle. First, fetch. It grabs an instruction from memory. Second, decode. It interprets the binary meaning using an intricate arrangement of logic gates. And third, execute. It actually completes the command. Fetch, decode, execute. Millions, billions, or even trillions of times every single second.
Now, this cycle builds into 2 completely different design philosophies. On one side, we have RISC architecture, or Reduced Instruction Set Computer. This uses highly efficient, very simple instructions. It's the whole reason your smartphone can last all day on a single charge. On the flip side, we have CISC, Complex Instruction Set Computer, which is used in traditional desktop PCs. CISC packs way more into a single complex instruction, which definitely demands more power, but it delivers heavy-duty multitasking capabilities.
Which brings us to part 2, when software turns lethal. What happens when the exact execution of those seemingly perfect instructions goes terribly wrong in the physical world?
This takes us into a pretty dark chapter in computing history with the Therac 25. Introduced back in 1982, this was a computer-controlled radiation therapy machine. Now, previous models relied on physical, foolproof hardware locks just to ensure they were safely configured before firing any radiation. But with the Therac 25, engineers made a fatal assumption. They removed those physical locks entirely, placing their ultimate trust solely in the software. And that overconfidence had absolutely catastrophic results. Due to a software flaw that could be triggered simply by an operator typing too quickly, the system allowed a high-current electron beam to activate without the protective X-ray target actually being in place. So instead of a safe intended dose of 200 rads, patients were struck with somewhere between 15,000 and 20,000 rads. To put that into perspective, a dose of just 1,000 rads is often fatal.
The human cost of this code is chilling. In June of 1985, a patient named Katie Yarborough was receiving treatment. When the machine fired, she experienced an intense electric shock. She told the technician, "I experienced a tremendous force of heat, this red-hot sensation. You burned me." Tragically, the medical staff assumed the machine couldn't possibly make that kind of error. Over 2 years, this exact software flaw caused at least 6 massive overdoses, leading to severe injuries and 3 deaths.
So, what exactly failed here? Well, it was a software flaw called a race condition. Because the operator typed commands faster than the system was designed to handle, the sequence of concurrent programming events just got totally jumbled. The software essentially told the machine it was safe to fire when the physical hardware was not ready. It's a deadly, tragic reminder that our digital architecture requires absolutely rigorous control, because microscopic code literally dictates our physical reality.
All right, shifting gears to part 3, crafting digital Apple reality. Simulating perfection. Because today, that exact same raw computational power is harnessed for a completely different kind of control, simulating flawless digital realities. Think about those iconic premium 3D product animations you see in Apple commercials.
Apple really demystifies the magic of their marketing by strictly adhering to a replicable set of rules. It's almost like a trade secret built entirely on minimalism. They use clean, solid backgrounds and incredibly intentional negative space to just remove all visual clutter. This gives your eye room to breathe and forces your attention entirely onto the premium aesthetic of the product. It's a highly calculated communication philosophy where less is actively more.
And they also rely heavily on physics-based motion. Objects in real life don't just stop and start abruptly, right? Animators use mathematical Bezier curves so that these products accelerate and decelerate with realistic weight and momentum. When a digital iPad rotates on screen, it feels heavy. Calculating this level of perfect, smooth motion across high-resolution 3D models requires massive CPU and GPU power to render every single frame. Part 4. The Rules of Cinematic Light. Demystifying the Magic. Creating a premium digital reality isn't just about smooth motion. It heavily relies on simulating the strict real-world rules of light.
The foundation of this cinematic look, whether you're on a real film set or simulating it inside 3D software, is the classic three-point lighting setup. First, you have the key light. That's your main, strongest source of illumination. Second is the fill light, placed opposite the key just to soften up those harsh shadows. And finally, the backlight, hitting the subject from behind to create this subtle halo effect that separates the digital product from its background and gives it true three-dimensional depth.
By just tweaking these simulated lights, animators can completely alter the mood. They can craft a high-key commercial, ignoring traditional lighting ratios, to create a very bright, shadowless, almost dreamy sequence. Or they can drop it into a low-key scene using a single strong key light with heavy shadows to evoke mystery and drama. And all of this emotion is achieved purely through mathematical instructions being processed by the CPU.
They even simulate specific real-world intensity rules, like the famous 4:1 lighting ratio. This basically means the intensity of light on one side of the subject is mathematically set to be exactly 4 times brighter than the other side. This hyper-precise control over digital photons gives a floating 3D object striking, lifelike dimension. It's literally millions of those Fetch Decode Execute cycles perfectly simulating the physics of light.
So, as we wrap up this explainer, let's take a step back. We've journeyed from the 16 billion transistors packed inside a modern chip to the tragic real-world consequences of a software race condition, all the way to the mathematical perfection of cinematic animation. We can marvel at how this microscopic architecture powers breathtaking digital art and life and death mechanisms alike. But it definitely leaves us with one final, lingering thought. In a world entirely built on these invisible cycles of code, who is really writing the instructions?